Welcome to Exercise 6, which centers on the digitization of bedding traces and their integration into a virtual outcrop model as planar features. In this exercise, we will explore and compare two distinct methods. The first method entails digitizing traces within Metashape and subsequently converting them into planar features using the OpenPlot software. The second method involves digitizing traces directly within OpenPlot, with the added benefit of real-time visual inspection to achieve the best-fit planar representation. In this exercise, the building and registration of the model have been omitted. We start with digitization of polylines in Metashape. First, we activate the Draw Polyline tool. Then, we digitize the bedding traces directly on the model. Polylines can be digitized onto the mesh, point cloud, and even directly onto the photos, provided the 3D model exists. The main advantage of digitization in Metashape is the high rendering speed of the software. The main disadvantage, instead, is that there is no idea of how accurately the trace being digitized corresponds to a plane. After digitizing the polylines as shapes, these shapes must be exported. Prior to exporting the polylines, it is essential to confirm the use of XY coordinates instead of latitude and longitude. To achieve this, navigate to the Reference tab, click on the Convert button, and then set the coordinate system to a projected system, such as UTM or a local system. After, we export the mesh and its textures into wavefront format. To do that, from the main menu, select Export and then Export Model. Choose the name of the file, and then, in the new form, set the reference system to UTM or local system, and press OK. Then we export the polylines in shapefile format. To do that, from the main menu, select Export and then Export Shapes. Choose the name of the file, and then, in the new form, set the reference system to UTM or local system. Now we close Metashape and we import mesh and polylines into OpenPlot. To import the polylines and convert them into best-fit planes, we begin by creating a new file and adding the tensor lambda1, lambda2, and lambda3 fields. These fields will be used to store the eigenvalues resulting from the planar best fitting of the imported polylines. To load the mesh, from the main menu we select Object, Import Mesh. We select the file, and then we apply the Load Only Mesh option and set the precision to single, which is an efficient choice for saving memory. We then import the shapefile. From the main menu we select Object, Import Shapefile, 3D Polylines, and we select the option of computing the best fit plane for each polyline. We eventually save the file in XML format. To view the result, from the main menu we select Plot, 3D View, and then we navigate the model. Now we want to view the attitude of the best fit planes derived from the planar best fitting of the polylines digitized in Metashape. From the main menu, we select Plot, Stereo Plot. In the StereoPlot window, we select Dip Domain, which is the name for the planar best fit element, and plot its poles. Poles to best fit planes plot on a great circle. The direction normal to it, that we call beta axis, is trending parallel to the orientation of the outcrop. Tensorial analysis returns the beta axis, which is the K3, and the direction of maximum concentration of poles, which is K1. The eigenvalue of K1 quantifies the extent of pole concentration around K1 within a 0 to 1 range. In this case, its value is 0.928. We now aim to eliminate from the dataset those planes that are associated with the polylines digitized in Metashape that exhibit an insufficient coplanarity. To accomplish this, in the main menu we select Data, Selection. And then we choose Tensor Lambda3 within the selection window. This field quantifies the coplanarity of points within a digitized polyline. A smaller lambda3 value signifies a closer adherence to the plane. We thus select only planes with low lambda3 values. Eventually, we apply the selection and replot data in the StereoNet. The best fit planes of the poles continue to align along the same great circle. The beta axis remains parallel to the primary outcrop direction. And the eigenvalue of K1 shows minimal variation. We now choose to manually exclude the outlier data point from our analysis. This involves using the selection drawing tool to isolate the central portion of the cluster, followed by applying the selection and replotting the data. As a result of this action, there is a slight elevation in the K1 eigenvalue, which increases from 0.928 to 0.967. We will now employ the second method for digitizing bedding surfaces, which entails the manual digitization process directly within the OpenPlot software. We begin by adding a new layer, called Manual, and selecting it. Next, we explore the model, actively searching for well-exposed planes. Once we identify a suitable candidate, we choose the Draw Polyline tool and start picking points of the trace. Eventually, if we are satisfied with the digitized plane, we finalize it into a lasting object by selecting the Create Planar Polygon button. We carry out the process of visual inspection and digitization for all the planes that appear to be promising candidates. After a sufficient number of bedding planes have been digitized, we plot them in the stereo plot. To compare the two methods, we first plot the planes derived from the automatic best fitting of the polylines digitized in Metashape. And then we plot the planes manually digitized directly in OpenPlot. Manually digitized planes exhibit a significantly higher degree of clustering and are less influenced by the outcrop orientation, yet the beta axis, which is the K3, aligns with the outcrop direction and closely resembles that of the automatically extracted planes. In summary, it's important to recognize that the orientation of planar geological features within a virtual outcrop model can be influenced by the orientation of the physical outcrop itself. This bias becomes especially pronounced when the traces of these geological features are digitized without proper visual control over the subsequent best fit plane calculation.